Hey everyone, so this video is gonna be, it's a chapter 10 video and it's on limiting reactant or limiting reagent. Let's go to our slides. So if you watched the video before on stoichiometry, these problems were easier in that you don't have to worry about the other ingredient in the chemical equation. So for example, this problem that asks how many grams of glucose, that's C6H12O6, can be synthesized from 58.5 grams of CO2 in photosynthesis. So how many grams of glucose can be formed from just this much CO2? We ignored the water, right? We assumed that there's enough water to react with the CO2 to form the glucose. So we didn't even care about whether we had enough water. We just assumed there was enough water. So this is a more simplistic stoichiometry problem. But we are now going to go into real world applications of stoichiometry because we are in the real world, right? So AKA that's limiting reagent, meaning there's going to be a reactant that runs out first, right? You don't always have, unlimited reagents, right? They're going to run out. And so you have to figure out which one runs out first because that's going to determine the maximum amount of product that you can make, right? That makes sense, right? Logically. Okay. But yeah, let's go. Let's go and define these terms. The reactant that runs out first, that's called the limiting reactant. The other reactant that is left is going to be in excess. So here's a hint for you on how you would know that you're faced with the limiting reactant problem. Is when you are given the amount of 2 or more reactants in a problem, you know it is a limiting reactant problem, okay? So look at your balance equation carefully, and is it giving you 2 amounts of reactants, 2 or more, right? And it has to be reactants, okay? Not products. That's why it's called limiting reactant, okay? So let's go back to the kitchen, and we're going to again, use that analogy. Remember, we're making a ham sandwich, and it costs us 1 slice of ham and 2 slices of bread to make 1 ham sandwich, right? And so now what we can ask is, in a real world problem, right, we don't have unlimited ham or unlimited bread. So let's say you only have 10 slices of ham in the fridge and there are only 10 slices of bread. How many sandwiches can you make? What's the maximum amount of sandwiches that you can make? Now, again, I bet you guys can do this in your head, right? Because the numbers are nice and round. So how many, so you ask yourself, basically, how many sandwiches can I make with 10 slices of ham? Well, I can make 10 sandwiches, right? And then you ask yourself, how many sandwiches can I make with 10 slices of bread, right? 10 slices of bread, well, I need 2 slices of bread for each sandwich. So I can only make 5 sandwiches, right? Okay. And this is how you show the work, right? Remember, you're using in your mind the mole-to-mole ratio that one sandwich requires 1 ham slice, right? So it's 1 to 1. That's why 10 sandwiches for 10 slices of ham, okay? And then in the second question, with the 10 slices of bread, you can only make 5 sandwiches because it's 1 to 2, right? You can make 1 sandwich from 2 slices of bread. Okay, so that's the reality, right? Is that, yes, you have enough ham to make 10 sandwiches, but you only have enough bread to make 5 sandwiches. So which one's your limiting reactant? It's the bread, right? That's what's limiting you from making an unlimited amount of sandwiches, right? That's the ingredient that's going to run out first, okay? So how many sandwiches do you make? Okay, of course, you're going to say 5, right? You're going to pick the lower number. It doesn't make sense to say I can make 10 sandwiches. Well, theoretically, you could have from 10 slices of ham, but you don't have enough bread. So in reality, you can only make 5 sandwiches, okay? So notice the process that we have to go through to get to the answer. We have to convert to the products first, okay? And then pick the smaller number, okay? So we pick 5 sandwiches. And so bread is then the limiting reagent. And what is the reagent that is in excess? Well, you'll have ham left over, right? So that if you buy more bread, you can make more sandwiches, right? So it's nice. It's actually quite, it's intuitive. It's obviously very logical. It's logic that's already inside you, right? But why am I, using this analogy is, yeah, it's going to be a little bit more, difficult when you get to chemical equations, right? So always keep this analogy in mind. That's the logic that you're going to use, even if, when we get to chemical equations, these ingredients or the chemical formulas are not familiar to you, right? You can still use the same logic. Okay, so ham is the reagent that is in excess. And how many ham slices do we have left? We're going to have 5 ham slices left, right? Because in making 5 sandwiches, you use 5 ham slices and you had 10 to begin with. Okay. Okay, so now when we go to chemical equations, or in real life when we're doing chemical reactions, we do, if we can use, we try to use the excess of a reactant. Why? Because one reactant might be more expensive than the other, and so you want to make sure that it's all used up. Or one reactant is really dangerous and you don't want to, have to handle it after the reaction, so you make sure that it's all used up during the reaction. So, in a combustion reaction, for example, O2 is always going to be in excess because you have an excess amount of oxygen gas, right? Whereas your phosphorus here is highly flammable, right? In combustion reactions, you have the one thing that's highly flammable that you want to use all up, right? So you always want to make that the limiting reactant. So when you're in the lab, that's something that you want to keep in mind, right? Okay, so let's do this now with real chemical equations and chemical reactants. So how many grams of solid aluminum sulfide can be prepared by the reaction of 10 grams of aluminum and 15.0 grams of sulfur? Okay, so let's make the balance equation first. Al plus S goes to Al2S3. Okay, if you're just given that, you need to balance the equation first. Remember, you always need to check. So I see it's unbalanced, so I'm going to balance it. 2 in front of Al, 3 in front of sulfur. Okay, and convert your gram to moles now, right? Remember that you need to figure out how much aluminum sulfide can be made from both of these reactants before you can pick the limiting reactant, okay? So right now you might want to say, oh, it's aluminum because 10 is smaller than 15. You cannot do that, okay? And I repeat, you cannot do that, okay? You need to solve the stoichiometry problem first before you can find the limiting reactant, okay? So we go through for each reactant, aluminum and sulfur, we go through the stoichiometry problem. Okay, so let's do it for aluminum first. 10 grams of aluminum, 1 mole of aluminum on top, 26.98 grams of aluminum on bottom. That's your molar mass from the periodic table. Then you go to sulfur, you do the same, right? 15 grams of sulfur times 1 mole of sulfur over 32.07 grams of sulfur. And that'll get you to 0.467 moles of sulfur, right? Then you calculate the moles of product by using the mole-to-mole ratio. So you're going to go from moles of aluminum to moles of the product, which is aluminum sulfide. So if you're just comparing aluminum and aluminum sulfide, your coefficients are 2 and 1. But 1's going to go on top because you desire aluminum sulfide. 2 is going to go on bottom, right? 2 moles of aluminum. So you end up getting what? Half of 0.371 or 0.186 moles of aluminum sulfide. Now you go and do the same thing for sulfur. 0.467 moles of sulfur. Apply the mole-to-mole ratio. 1 mole of aluminum sulfide on top. But now you're looking at sulfur. That's 3 moles of sulfur will go on bottom. And so you get 0.156 moles of aluminum sulfide. Then what do? You pick the small smaller one, right? Remember how the logic works. You have enough ham to make 10 sandwiches, but you ran out of bread. You can only make 5 sandwiches from that. That's why you pick the smaller number. Same thing here. You have enough aluminum to make 0.186 moles, but you only have enough sulfur to make 0.156, right? So obviously, in reality, you can only make the smaller number. You can only make 0.156 moles of aluminum sulfide. Therefore, your reactant is sulfur, right? Sulfur is the limiting reactant, which is the reactant that makes the smallest number of products, okay? And then after that, then you can, once you figure out the limiting reactant and how much you can actually make, then you transform that into grams. So pick the smaller number, and then you use the molar mass of aluminum sulfide with 150.16 grams on top to get to your grams of aluminum sulfide, right? Okay. So in summary, when you're solving limiting reactant problems, remember that step 1, you want to balance the chemical reaction first. And step 2, you're going to convert to grams to mole if applicable. Step 3, you will calculate the mole product that can be made from the mole of each reactant. Use stoichiometry. Step 4, you're going to compare which reactant makes fewer mole product, and that is going to be your limiting reagent. Step 5, use the mole product from limiting reagent to convert to grams of product. These are going to be the potential pitfalls that you're going to want to avoid as, you know, a beginner in stoichiometry. Remember that the limiting reagent is not the reagent present in fewer moles. Okay, so let's go back to see what I mean. Remember, and the other pitfall, right? The limiting reagent is not the reagent present in lower mass. So remember when we started the problem, we had 10 grams of aluminum and 15 grams of sulfur, right? Like like sort of a gut, reaction is to be like, oh, maybe the aluminum is the limiting reactant because it's less in grams, right? 10 grams is less than 15 grams. But remember, that wasn't true. It was sulfur that was the limiting reagent, right? So you can't tell, okay? You cannot tell from the prompt. You have to do some math first. You have to go to how many products can be made before you can figure out the limiting reactant, okay? So very important there. All right, so let's do it now. Practice on limiting reactant. And remember my tip for limiting reactant type problems, how you can tell is they're going to give you 2 or more amounts of the reactant. So let's read how many moles of Si3N4 can be made from 1.20 moles of Si and 1.00 mole of N2 in the reaction 3Si plus 2N2 goes to Si3N4. Okay, so what are my 2 reactants? Si and N2. Oh, and look at that. It gives me amounts for both of them, right? For 2. I know it's a limiting reactant problem, and I have to solve 2 stoichiometry problems before I can find the limiting reactant, okay? So the first stoich problems I have, so let's do this on the board. I'm gonna write it down first. Okay, so there's my equation, and it's asking, right, how many products? So you can think of this as like the ham sandwich, right? And this could be your ham, and this your slice of bread, right? Now it's 3, 2, and 1, and it's asking how many products, right? So how many sandwiches can be made from its ingredients? 1.20 moles of, let's say, ham, 1 mole of bread, right? So something like that in our analogy. So what that means is we got to figure out how many sandwiches, right? Or how many Si3N4 we can make from each of these before we can figure out how much can be made, right? Because we need to figure out which one's going to run out first. Okay? So let's start with Si, okay? And we need to see how much Si3N4 we can make from Si, okay? So that's our A, that's our B now, right? So 1 mole of Si3N4 on top, right? And then 3 moles of Si on bottom. So that mole of Si can cancel. Okay. So 1.2 divided by 3, that's going to be 0.400 moles of Si3. Why do I write the 2 zeros? Because I need 3 sig figs from this number, right? So 1.2 divided by 3. Okay. Then we have 1.00 mole of N2. And how much Si3N4 can we make from that? So 2 moles of N2 is going to be on top, while 2 moles, sorry, 1 mole of Si3N4 is going to be on top, 2 moles of N2 on bottom, right? So you see there, I was like, I made a mistake, but I could tell that I made a mistake because I was like, wait a minute, I want moles of Si3N4 on top, right? So that's the beauty of the method that we use, is that if we make a mistake, we can actually quickly tell that it's that we made the mistake. Okay, so then 1 divided by 2 here, we're going to have 0.5. Again, 3 sig figs, 0.500 moles of Si3N4 in this case. Okay, so now you can see that what we're saying here is if from the moles of Si, we can make this much Si3N4. From this much N2, we can make 0.5. So in reality, we can only make how much? Always pick the smaller number. So this, we don't even care anymore, right? That's our answer, right? Is 0.400 moles of Si3N4. Again, always pick the smaller number. Okay, let's go back to our slides. All right, we'll move on now. We're going to talk about also theoretical yield, actual yield, and percent yields. So here's an example of a percent yield. Percent yield is used to measure the efficiency of the reaction, and sometimes it also measures how well you perform the reaction, right? So here's an example. Let's say that you had 12 slices of bread and 6 slices of ham, but you end up only making 5 sandwiches. What is your percent yield of sandwiches? So from the balance equation, right, remember this, theoretically, from 12 slices of bread and 6 slices of ham, you could have made 6 sandwiches, right? But your actual yield is 5. You can only make actually 5, okay? So you must have dropped some bread, or maybe you broke it, or, you can't make sandwich with that bread. So you ended up only making 5 sandwiches for whatever reason, okay? So now to measure your percent yield, which is the efficiency at which you did this reaction, you're going to take the actual yield, 5, and you divide by the theoretical yield, what you should have made, right? If everything went perfectly, that's the denominator, times 100, you get 83% yield, okay? So you only made 83% of what you could have made, right? And of course, there are many reasons why the percent yield is less than 100. You may have dropped it. Maybe you toasted the bread and you burnt it. Who knows, right? But the percent yield is measuring that efficiency. Okay. So the theoretical yield is defined as the maximum amount of product that you can make in a perfect situation. So this is a calculated yield, right? And that's what we've been doing when we were doing these problems, stoichiometry problems. The numbers that we got at the end, they were theoretical yields. Okay. Now, how is the actual yield different? Well, it's actually what you do in real life, right? So you go into the lab and you perform the reaction, and you measure how much product you obtain. So actual yield is in real life in the lab. So it cannot be calculated, right? It can only be obtained by you going and doing the reaction. Okay. So that's how we are able to get a percent yield. That's the meaning of it, right? Is to measure that efficiency. So you take the actual yield on top, you divide by the theoretical yield on bottom, times 100%, and that'll give you your percent yield. So why not? Why can't you get 100% yield all the time? Well, in reality, you can never get 100% yield. Just think back to, anytime that you make anything in the kitchen, um, you know, some things will always get lost, right? Let's say that you're putting mayonnaise on your sandwich. Well, some of the mayonnaise is stuck to the knife, right? You don't get all of the mayonnaise that you got out of the jar onto your sandwich, right? That's just the nature of things, right? Is that you can never reach 100% yield. You can reach a high yield, you could be 99%, but you can never be at 100. And so there are multiple reasons why you can't do that for chemical reactions. One is reversible reactions, which means once you get an appreciable amount of products, those products can react with each other to go back to reactants. Or you can have side reactions, right? Meaning you can have byproducts. So you're not only getting what you need, but you can also have multiple products that will lower your yield. You can also have slow reactions. So, you're not going to want to have to wait for your reactions. You may want to just stop the reaction so that you can harvest your product. You don't want to wait years and years, right? And so you're not going to get 100% yield. And then the last one, right? Loss of product during separation or purification. That's like the mayonnaise case on the knife, right? As you're collecting your product, it's always going to be stuck to the side of the glass or stuck to your spatula. Something's going to be, happening that you're not going to get 100% of your product. Okay, so let's do some example problems with limiting reactants some more, right? So in this example, it's asking, what is the limiting reactant and the theoretical yield when 0.552 moles of aluminum reacts with 0.887 moles of CO2? Okay, again, I'm going to put it on the board. TY stands for theoretical yield. Okay, so remember that tip I gave you guys? How can I tell that it's a limiting reactant problem? Well, obviously here it tells you, right? But what if it didn't tell you? How can you tell again? Because it's giving you amounts, right, of two reactants, two or more reactants. Okay, so you're gonna have to solve two stoichiometry problems, right? One starting from aluminum and going to AlCl3, and the second from Cl2 going to AlCl3. Okay, so let's do that. Let's start with 0.552 moles of aluminum first. We need to get to the products, right? We always need to get to the product first, remember, before determining the limiting reactant. So 2 moles of AlCl3 on top and 2 mole of Al on bottom. So that can cancel. So we get 0.552 moles of AlCl3. Okay, then we go to CO2, 0.887 moles of Cl2. Again, we need to go all the way to product. So 2 moles of AlCl3 over 3 moles of CO2. Okay. And we'll have 0.591 mole of AlCl3. Okay, so remember what we're doing here, right? Logically, what we're doing is we're saying from this many moles of aluminum, I can make this much aluminum chloride. And then from this many moles of Cl2, I can make this much aluminum chloride, right? So how much aluminum chloride can I actually make? Always the smaller number, right? So not that one, it's gonna be this one. And so this is what we say is the theoretical yield in moles. Okay. But when it's asking for theoretical yield, it probably wants it in grams, right? Because it wants a mass. Okay. So we will then take this number and convert it to grams. Okay. And so what is the limiting reactant? Well, what's the reactant that made this much aluminum chloride? It's the aluminum. So you say aluminum is the limiting reactant. And then for your theoretical yield, you take 0.552 moles of aluminum chloride and you convert it to grams, right? So 1 mole of AlCl3 on the bottom, and then we're going to get the molar mass of AlCl3. So that's 133.34 grams of AlCl3. So we get 73. Let's check the sig base. We need 3. So 73.6 grams of AlCl3. That's our theoretical yield, right? So remember what theoretical yield means. If everything is perfect, right, we should be able to make 73.6 grams of aluminum chloride from these conditions, right? From our limiting reactant. Okay. All right, let's go back to the slides. Check our answers here too. Good. Okay, let's do this problem. When 11.5 grams of carbon are allowed to react with 114.5 grams of Cu2O in the reaction below, 87.4 grams of Cu are obtained. Find the limiting reactant, the theoretical yield, and the percent yield. Okay. So the limiting reactant, right, in the last problem, we did limiting reactant and theoretical yield. The only extra thing we have to do in this problem is finding the percent yield, right? So remember what percent yield is? It's measuring your efficiency. So percent yield is actual yield over theoretical yield times 100%. Okay. So your actual yield, guys, is always going to be given to you. Right? Otherwise, you'd have to go into the lab and make it yourself. And obviously that's not happening, right? So the actual yield is always given to you in the problem. So guess where it is in this problem? It says here, 87.4 grams of copper are obtained. Well, what's copper? That's the product. So it's telling you that somebody did this, right? Somebody did this for you and obtained 87.4 grams of copper. So that's your actual yield. So now all we need is the theoretical yield, which we're going to calculate, right? And then we're going to get the percent yield. Okay, so we'll do it on the board again. Let me copy this down. Okay, so here we have the balance equation. Cu2O plus C goes to 2Cu plus CO. 11.5 grams of carbon react with 114 grams, 114.5 grams of Cu2O, 87.4 grams of Cu is obtained. Find the limiting reactant, theoretical yield, and percent yield. Okay, so remember, we need to get to copper, right? That's our product. There is another product, but it doesn't talk about it in the problem, so don't worry about it, right? We just need to get to Cu from each of the reactant, right? C is a reactant, Cu2O is a reactant, okay? So start with 11.5 grams of C, okay? We need to go to mole of C, right? It's a roadmap, okay, roadmap. So 1 mole of C over 12.01 grams of C, okay? And then for mole A, we need to get to mole B, which is a mole-to-mole ratio, right? Between carbon and copper. So we need 2 moles of Cu on top and 1 mole of C on bottom. And at this point, I would just calculate it in moles first, okay? So let's punch that in. $1.92. Well, let's keep more sig figs since we're not done with the problem. So I will keep 4 sig figs for now. Okay. And then we go to the other reactant, 114.5 grams of Cu2O. We need to get to moles of Cu2O first. So we need the molar mass here. We need to calculate that. It's going to be 143.09 grams of Cu2O. Okay. And then we need the mole-to-mole ratio between Cu2O and Cu. Okay, so 2 moles of Cu on top still. Now it's 1 mole of Cu2O. It's 1.600. Again, I'm keeping 4 sig figs. Okay. And then, of course, between these two numbers, remember, we're going to pick the lower one. Okay. So that's going to be our theoretical yield in mole, but we should change it to grams. So molar mass of copper is 63.55 grams, right? And that goes on top. We want grams on top. 1 mole of Cu on bottom. Okay, so 3 sig figs, 102 grams of copper. That is our theoretical yield. Okay. The limiting reactant we know is, right, what produced the smaller number is the Cu2O is the limiting reactant. And now the percent yield is our last thing. Percent yield is equal to actual yield divided by theoretical yield times 100%, right? So what is our actual yield? 87.4 grams. Divide by the theoretical yield is 102 grams. So the grams cancel times 100%. .7%. Yeah. Okay. So, right, limiting reactant, theoretical yield, percent yield. Okay. Okay, let's go back to the slides again. See our answers. Check our answers. .9. Very good. Okay. Let's do one more problem here. How many grams of N2 can be made from 9.05 grams of NH3 reacting with 45.2 grams of CuO? We got the balance equation, which again, I'm going to write on the board. Okay, and it says if 4.61 grams of N2 are made, okay, what is the percentage? Okay, and the conditions was 9.05 grams of NH3 was reacted with 45.2 grams of CuO. So what is the percent yield? Okay, so here we go. All right. First, we need to get from ammonia to N2, right? So remember, it's giving you the actual yield here. So what we need for the percent yield is the theoretical yield. So we need to get the stoichiometry problem. So we need to get from NH3 to N2, okay? So we have grams of NH3 here. All right, use your roadmap. You got to go to moles of NH3. Which is 17.03 grams of NH3. Okay, and then from moles of NH3, we need to go to N2, 2 moles of NH3 on bottom, right? 1 mole of N2 on top. And we'll stop there at the moles. Get the moles first. And again, keep at least 4 sig figs here, okay? So what we're saying is from 9.05 grams of ammonia, we can make this many moles of N2. And now we do it again with CuO, 45.2 grams of CuO. So we'll do 1 mole of CuO on top and molar mass of CuO, 95.55 grams on bottom. And then molar mole ratio, CuO to N2, right? So 1 mole of N2 on top, 3 moles of CuO, right? Where do I get the 3? From the coefficient. Okay, and get that number. Zero 0.1577 mole of N2 can be made from 45.2 grams of CuO. Okay, so again, what do? We pick the smaller number. Okay, which means our CuO is the limiting reactant. This is our theoretical yield, but we need to get it into grams in order to get the percent yield, right? Because the actual yield is in grams. So 1 mole of N2 is on bottom, 28.02 grams of N2 on top. So we get 4.42 grams of N2. So this is going to be our theoretical yield. So to get percent yield, remember it's actual yield over theoretical yield times 100%. So actual yield is 4. Let's see here. 4.42, 4.61. Okay. Okay, so right here, we can see that a calculation might be off. Because my theoretical yield is smaller than my actual. Okay, I see the issue. This molar mass was off. Oh, okay. This molar mass was off. So that's gonna change my mole number here. Okay, so that'll change this. So my actual yield or my theoretical yield is now 5.31. Okay, yeah. So that was the mistake, was I had the wrong molar mass of CuO. 79.55, that should have been. So let's quickly recalculate just to double check one more time. Okay, that's the right number. And then we multiply by 28.02 to get this. Okay, good. So now our actual yield, 4.61 grams over theoretical 5.31 grams times 100%. Is 86.8% yield. Okay. All right, guys. So again, go and practice. If you need to, watch more videos, more examples, or rewatch these, in a slower way. Make sure that you get it and then go practice. I'll see you in the next video.